Greetings, I'm Farooq from IFT Back. Forwarding large messages through libp2p Gossipsub protocol results in noticeable performance deterioration. We identified some fundamental reasons that are responsible for this behavior. Based on these findings, we proposed Gossipsub version 1.4 for improved large message handling. The proposed modifications take effect when handling large messages, so the Gossipsub performance remains unchanged for small messages, whereas a superior performance in terms of latency and bandwidth utilization is achieved for large message transfers. In today's talk, we mainly discuss Gossipsub version 1.4 proposal. First, let's have an overview of the Gossipsub protocol. Here, every peer connects to the other peers, which is three in this case, to form a full message mesh. On receiving a message, every peer forwards that message to its full message mesh members, except the ones from which that message was received. So this message propagates through the entire network through this process. Generally, in ideal conditions and with a fair value of D, this full message mesh is sufficient for disseminating messages to the entire network. However, to ensure network-wide reachability of messages, Gossipsub also makes use of a gossip or a metadata-only mesh where every peer announces the IDs of these seen messages to other peers, which are not part of its full message mesh. On receiving these IDs, which we call I have announcements, any peer can request for any unseen messages using I want request. And the sender obviously can reply back with the message to that peer. The use of I have and I want messages basically have three fundamental purposes to serve. First, it ensures reachability in the case of network partitions. Number two, it ensures resilience against non-conforming peers. And most importantly, it can speed up message dissemination to distant peers. In Gossipsub version 1.0, replying to I want messages was mandatory and there was no limit on the number of I want requests a peer can make. So that could potentially overwhelm many honest senders. So the security hardening extensions in version 1.1 use peer budgeting to control the number of I want requests that can be made. And also replying to I want requests is now made optional. That also means that any peer now can make multiple requests for the same message ID. This arrangement works fine for smaller messages, but for very large messages, this simply increases the number of duplicates in the network. And also, these I want requests are usually made to the peers who are on the optimal paths or who are actually the early receivers and are actually responsible for quickly disseminating the message to the network. So it actually can indirectly also slow down the message spread in the network. So basically, the problem that we face is as the message size increases, we get to see very steep rise in message dissemination latency, and also we notice a steep rise in fluctuations in this end-to-end message dissemination time. Same is the case with bandwidth utilization. We see a steep rise in number of duplicates or in overall bandwidth utilization of the network. First, let's see this very basic message transmission time estimation. We can ignore all the processing delays and even the transport layer delays introduced. We can say that message sending to one single peer can complete in L over R plus P time, where L represents the message size and R is the data rate. P is the propagation time for that message to reach to the next hop. Assuming 100 Mbps bandwidth and 100 millisecond latency, sending to one peer a 10 kb message, it can complete in 100.8 milliseconds, where 100 milliseconds is actually the message dissemination latency, a message propagation time actually. But this time jumps from 100.8 to 180 for sending 1 MB message to a single peer. In case of a full message mesh with D, which is set to 8, for example, this message transmission to the full message mesh can complete in approximately 740 milliseconds. In practice, this tau D rises by several hundred milliseconds, mainly due to the transport layer constraints, where we limit maximum inside bytes based on the congestion window. So we carried out a small experiment where we transmitted 12 1 MB messages. Every row represents one message. This is the maximum message. This is the overall message dissemination time, and this is the average of the times for each of the messages. Okay. Now here we represent the message spread. We simply sample the time over 100 millisecond interval. So this is the state of the network, the number of messages received after 100 milliseconds, after 200 milliseconds, after 300 milliseconds. We can see the message dissemination for first message to the full message mesh completed approximately after 1500 milliseconds. Same is the case for second message. After that, since the congestion windows at the peers increase a little bit, so this message dissemination to full message mesh, the time increase a little bit, but still we can see a significant time is required for sending messages to the full message mesh members. And interestingly, receivers are not aware of the message IDs that they are receiving during this message dissemination time. And during this time, if any of the peers already receiving this message get to receive an I want request, simply makes I have announcement, it simply makes an I want request for that message. So this is a representation where we transmitted approximately 12 messages in a 1500 peer network, and we distributed the bandwidth between 50 and 150 Mbps, similarly latency between 40 and 130 milliseconds. And we get to see this situation. As the message size rises, we can see the maximum number of I want requests made by a single peer. It also rises significantly. Remember, we have only 12 messages that were transferred to the network, and we see up to 160 or close to 160 I want requests created by one single peer, whereas the average number of I want requests was reasonably small. At the same time, the total number of I want requests generated in the network can be, the legend is on the right hand side, can also be seen with this yellow line here. Now, interestingly, most of these I want requests are sent to the early message receivers. Those early message receivers are actually the optimal path peers. So, with this additional responsibility to fulfill, the message dissemination time in the network also increases. For example, we disabled I want messages in the network just to see the impact on the message dissemination time. And we see here that the same message gets disseminated in the network with a reasonably lower message dissemination time. But obviously, we cannot disable I want messages in the network as they are very important for the resilience of the network. But now, at least, we establish one fact that I want messages are no longer a performance improvement measure, but yes, they are still needed for the resilience in the network. Another problem that occurs with this slowed message propagation is the number of duplicates. Ideally, there should be approximately D by 2 duplicates in the network if send and receive operations are mutually exclusive. But we notice that there are very large number of duplicates that are transferred in the network, and also the number of duplicates, it rises from nearly 6 duplicates per message per peer to approximately 8 duplicates per message per peer. And out of that, approximately 2 duplicates per message per peer are contributed on an average from the I want messages. The use of I don't want messages lower these duplicates to some extent, but we don't see a significant drop in the number of duplicates in the network. The fundamental reason for this is to minimize the number of duplicates or to increase the effectiveness of I don't want announcements. A sender must receive and process that I don't want message before it starts sending the message in the network. Interestingly, some studies suggest that in most of the cases, the first message arrival time and the first duplicate arrival time is usually bigger than the overall message dissemination latency within the network. But even then, we don't see much effectiveness because the problem lies in that message reception time. During that large message reception time, we get to see overlaps in, or we get to see that many senders start sending simultaneously to the same peer. So, basic idea is we want to enable peers to quickly learn that they are receiving a message. For example, if peer A is sending a message to peer G, now peer G should immediately get aware by some mechanism that peer A is already sending a message to peer G. So we use message preamble, which is a small message just announcing the ID of the message that we are transmitting to peer G. So any other peer, if it sends an I have announcement to peer G, it simply gets to see that it has already received a preamble from peer A. So it can defer receiving that, or it can defer sending an I want request for that message to peer I. That is one part of the solution. At the same time, we can further take this solution to further minimize the number of duplicates in the network. For example, once peer G received this preamble from peer A, this peer G can immediately inform its full message mesh members that it is already receiving message ID X. So peers F and H, which are its full message mesh members, they can defer sending the same message to peer G. Obviously, when this message reception from peer A to peer G completes, peer G can send an I don't want announcement to its mesh members. That I don't want basically informs these mesh members that peer G has already received the message. Otherwise, peer H or peer F can obviously start sending the message to peer G if a certain time interval is expired. Obviously, we can compute that time interval by the length of the message announced in the message preamble. One more discussion. Yes, this preamble can be exploited by some non-conforming peers. For instance, in this particular case, peer A can send a preamble to peer F, and it can also start slowing down the message transfer time, message transfer to peer F. In that case, peer F can definitely use peer scoring, negative peer scoring for peer A, and also if the message transfer time computed from the length of the message in the message preamble, if that time expires, peer F can obviously request for the message from its other mesh members, whoever is sending that message to peer F. So we have actually two uses to make from this message preamble. Number one, message preamble enable peers to quickly learn about ongoing message receptions. So any peer, it can simply defer message reception for that message. We can defer I want request for that ongoing transmissions, and defer interval can definitely be computed from the message length. Number two, any peer will make only one I want request at a time for any I have announcement that is meant for a larger message. On the other hand, we also use I am receiving messages, which are generally introduced to complement I don't want announcements, because in case of I don't want, we can announce only after we have finished receiving that message. In case of preamble, we can immediately announce that we are receiving the message. So as soon as we start receiving the message, we can send I'm receiving announcement to our mesh members so they can defer sending that same message to us. When applied, this thing to a network with varying message sizes, here we experimented this approach with different mechanisms. For example, in this bar, here we have a situation where we use I'm receiving message only, and we do not limit I want requests to one on the basis of message preamble. And also we have this situation where we only limit I want requests to one based on the message preamble, and we don't announce I'm receiving messages to our mesh members. And then we have this hybrid solution, this merger, where we use the benefits from both the I'm receiving message and also from I want optimization. So the gain that was achievable by both the approaches is actually accumulated to this merged approach. So we can see up to 60%, 65% bandwidth reduction is seen for large message transfers. At the same time, we also get to see that this approach get to preserve latency by reasonable time for large message transfers. It is also important to notice that we can preserve latency only when we can get to minimize the workload at the optimal path tiers. In case of I don't want announcements, usually the duplicates that we reduce are on the later phases of the message dissemination. So that message usually does not have much impact on the message dissemination latency. Also, I'm receiving message does not have much impact on the message dissemination latency. But I want announcements are usually sent to the peers that are on the shortest path. So I want announcements actually get to achieve maximum preservation in message dissemination latency. And when we merge these approaches, we get to see a reasonable reduction in message dissemination time represented by this blue bar. Also, looking at the number of duplicates, we get to see that as the message sizes increases, we tend to lower the number of duplicates because obviously large message transmission completes in a significantly larger time. And by that time, we had already transmitted the I'm receiving message to our mesh members. Thank you.